Greetings and welcome back to the Math Olympiad lecture series. This is the lecture series for the senior section and it's a continuation of the previous lecture 2A on trigonometry, and we'll be looking at a selection of interesting problems for your practice. Let's quickly recap the Trigo identities that you will need for this video. You should be aware of the complementary angle formulas, the formulas relating the trigonometric ratio of obtuse angles to the basic angles, as well as if the angle was in the third or fourth quadrant. We will also need the reciprocal trigonometric ratios and their definitions. You should be familiar with the trigonometric ratios for special angles, including 30, 45, and 60 degrees, the Pythagorean identities, the addition angle formulas, as well as the double angle formulas. Lastly, you'll also need the sum to product and product to sum formulas that I've gone through in the last video. Question number 1. Evaluate Part A, tangent 1 plus tangent 3 plus tangent 5 all the way to plus tangent 179. Part B, same thing but product, so tangent 1 times tangent 3 times tangent 5 all the way to times tangent 179. And in part C, sine square 1 plus sine square 2 plus all the way to sine square 90. Pause the video here and give these questions a good try. So the trick to these summations and products are to find the right pairs that will hopefully kill each other off like the Squid Games. So in part A, we're going to use the obtuse angle formulas for tangent. If we pair up tangent 1 degrees and tangent 179 degrees, notice that tangent 179 degrees is in the second quadrant and we can change it to the first quadrant and its basic angle is 1 degree. So we'll get tangent 1 degree minus tangent 1 degree, which gives us 0. Similarly, we can do the same for tangent 3 and tangent 177, and all of them will pair off and kill each other off. Hence, the final answer will be 0. In part B, we're going to use the complementary angle formula. So tangent 90 degrees minus theta is equals to 1 over tangent theta. So we're going to pair 1 degree with its complementary angle 89 degrees. And when we multiply them together, we'll get tangent 1 degrees times 1 over tangent 1 degrees. The tangent 1 degrees cancel out and we get 1. So we'll find all the complementary angle pairs and we'll multiply them together and they each produce 1. Notice that there's one guy who's not included. He has no pair. It is 45 degrees, but that's a special angle and tangent 45 degrees is equals to 1. So you can see that when we multiply everything from tangent 1 all the way to tangent 89, it's just 1 times 1 times 1 all the way. So we're still left with 91 to 179. Again, we're going to find their pairing. So tangent 91 and tangent 179, we convert them both into its first quadrant counterpart, which will be negative tangent 89 degrees times negative tangent 1 degrees, and that still gives us 1. And you'll see that we can do this pairing all the way, and everybody multiplies together to give us 1. Again, there's one guy we forgot. It's tangent 135 degrees, and he gives negative 1. So it's a lot of 1s and only one negative 1, so the final answer is negative 1. In part C, the pairing will also be by the complementary angles. So we'll pair sine square 1 with sine square 89. Using the complementary angle formula that states that sine of the complementary angle gives us cosine of that angle, we can convert sine square 1 plus sine square 89. The sine square 89 becomes cos square 1. Then using the Pythagorean identity, we can sum up sine square 1 and cos square 1 to give us 1. We'll repeat this for all the complementary angle pairs, but we need to also remember what we have left. So altogether we have 44 pairings of complementary angles, but we have forgotten 2 numbers that were never paired up. So we have forgotten sine square 45, we need to remember that. And since sine 45 is a special angle, which is 1 over square root 2, sine square 45 will be half. And the other angle that we have not considered is 90 degrees. So don't forget to calculate sine square 90. Sine 90 equals to 1. So sine square 90 is also 1. So adding them up together, we'll get 45.5, and that's our final answer. So for part A, we get 0. Part B, we get -1. And part C, we get 45.5. Question number 2. Evaluate this trigonometric sum. Pause the video here and give this question a good try. Now there's a neat little trick when we see something like 1 plus tangent A over 1 minus tangent A, because this closely resembles the addition angle formula for tangent. Now if we just add a times 1 in the denominator, we can convert the 1 into tangent 45 degrees and then apply the addition angle formula to give us tangent 45 degrees plus A. And we'll be using this useful identity throughout this question. So if we look at the first term and the last term, we can convert them using the identity into tangent 47 degrees and tangent 133 degrees respectively. And we're going to choose this pair to add together. Now we use the second quadrant formula that states that tangent of 180 degrees minus A equals to negative tangent A. This converts tangent 133 degrees into negative tangent of its basic angle, 47 degrees. And this will cancel out to give us 0. Now this will work for all the supplementary angle pairs. And if we add them all the zeros together, we're obviously going to get 0. So the final answer is 0. Question number 3. Find the value of this trigonometric sum. Pause the video here and give this question a good try. Now in this question, before we pair them up to eliminate stuff, we can do some matching of identical terms to cut down the total workload. Notice by using the obtuse angle formula for sine of 179.5 is the same as sine of 0.5. So these two terms are identical. Likewise, if we use the obtuse angle formula for tangent 179.5 is equals to negative tangent of 0.5. Of course, if we square both terms, they will be identical. So let's just check with the third and fourth last terms with the third term and fourth term. See that these two terms are identical. These two terms are also identical. In other words, I only need to compute this sum from 0.5 degrees to 89.5 degrees, then double the final result. Now to start eliminating and simplifying some stuff, we can use the complementary angle formula for sine squared 0.5. We note that sine 0.5 will become cosine of 89.5. So I have 1 over cos squared 89.5. And that's where I can use the secant identity, change it to secant squared 89.5. And then I'll use the Pythagorean identity for secant. And I will change this to 1 plus tangent squared 89.5. And this is nice because at the very end, I have a tangent squared 89.5 to deduct. So 1 plus tangent squared 89.5 minus away tangent squared 89.5, I get 1. And this will also apply to every pair of the sine squares and tangent squares as shown. So they will all eliminate and all turn to 1s, and there are 90 pairs of them. Then don't forget to times 2 because we're doing it for 2 sets. So the final answer will be 180 degrees. So did you get the answer? Question number 4. Let m be the largest positive integer such that cos square x minus sin square x plus sin x equals to m over 888. That this equation given has a real solution. Find this value of m. Pause the video here and give this question a good try. First, we're going to apply the Pythagorean identity and we're going to convert this cos square x into 1 minus sin square x. So notice that we have a quadratic in terms of sin x. So if you have difficulty seeing the quadratic, you might want to substitute, let's say, p equals to sin x. Then to show that it has a real solution, you can either use the discriminant method, set the discriminant to be greater than or equals to 0, or you can try completing the square. So I'm going to do the completing the square. You can try the discriminant method on your own and you'll see that it's the same answer. So what I'll do first is I'll bring all the sine square terms to the left-hand side, as well as all the sine x terms. Then all the constant terms go to the right-hand side. Now to complete the square on the left-hand side, I need to add 1/4 square. So I have to do that to the right-hand side as well. So the left side can be factorized into sine x minus 1/4 whole thing squared, and that'll be equals to the constant stuff, which is 9/16 minus m over 2 times 888. Now, for this to be having real roots, the square has to be a positive number or 0, so it has to be greater than or equals to 0. That means the constant stuff on the right-hand side also has to be greater than or equals to 0. So just solving the inequality there will give us m to be less than or equals to 999. Hence, the largest possible value of m would be 999, and that's our final answer. Question 5. Find the value of 8 over sine 2a plus 12 tangent a, where a is an acute angle between 0 and 90 degrees. Pause the video here and give this question a good try. Now, the strategy here is to convert this entire expression into the same Trigo ratio. So in this case, we're going to try to convert it into tangent a. So we can start by applying the double angle formula for sine 2a. So this gives us 2 sine a cos a. Cancel the 2 common factor. That gives us 4 over sine a cos a. Now, here's a little trick. We can change the 4 into 4 times 1. And what is that 1? We can change that 1 into sine square a plus cos square a. Because by the Pythagorean identity, sine square a plus cos square a is equals to 1. So we're going to split this up into 2 fractions. So the first fraction, 4 sine square a over sine a cos a, cancels out to give us 4 tangent a. And the second fraction, 4 cos square a over sine a cos a, gives us 4 over tangent a. And plus the 12 tangent a behind, we have successfully converted the entire expression in terms of tangent a. Now we want the minimum value of this. So it might not be easy to see this, but let's just substitute x equals to tangent a. And we have an equation y equals to 16x plus 4 over x. And we want to find the minimum value of y. So this becomes a calculus question. We can find the minimum value by differentiating the y with respect to x. This gives us 16 minus 4 over x squared. And for the minima, the gradient has to be 0. So we sub in 0. And x has to be plus or minus 0.5. Now at this point, we take note that a is an acute angle. Therefore, tangent a can take any positive values, including but not including 0. So x has to be positive 0.5. So when we sub that in, the minimum value will be 16 times 0.5 plus 4 over 0.5, which gives us 16. Alternatively, you can also use the AMGM inequality. 16x plus 4 over x looks very much like the arithmetic mean. You just need to take out the over 2 and you can perform the AMGM inequality, but I won't go through that solution. All in all, we have 16 as our final answer. In question 6, we have a figure that comprises of 3 right-angled triangles such that angle GCB, ACE, and DFE are the 90 degrees. And we have 3 equal angles, GBC, EAC, and EDF are all, we'll just label them theta degrees. And we're given 3 lengths, GB equals to 6, AE equals to 10, and DE equals to 8. And we want to find the maximum possible value of the areas of triangle ABC plus the area of triangle CDE. Pause the video here and give this question a good try. Notice that we have been given 3 right-angled triangles with a reference angle of theta with known hypotenuses. This allows us to find the respective base and heights of these 3 triangles using the sine and cosine ratio. Starting with this green triangle, we have a base of 10 sine theta and a height of 10 cosine theta. Next, for this blue triangle, the base would be 6 cosine theta, and for this pink triangle, the height would be 8 cosine theta. Now we know the base and heights of triangles ABC and CDE. We can find the area of these two triangles using half base times height, and that will give us 30 cos squared theta for triangle ABC and 40 cos theta sine theta for triangle CDE. Now, to find the maximum possible area, we first have to do some trigonometric identities. So the first thing we're going to do is we're going to work on triangle ABC. We're going to subtract 15 and add 15. This way, the first two terms, 30 cos squared theta minus 15, we can factorize out a 15, and you'll see that we have the identity for the double angle for cosine. So we can convert 2 cos squared theta minus 1 into cos 2 theta, and now triangle ABC is just 15 cos 2 theta plus 15. For triangle CDE, we will use the double angle formula for sine. Sine 2 theta is equals to 2 sine theta cos theta, so the area will become 20 sine 2 theta. So the combined area S will be equals to 15 cos 2 theta plus 20 sine 2 theta plus 15. Now, to find the maximum area, there are a few methods. We're going to use the R formula first. So the R formula states that A cos theta plus or minus B sine theta equals to R cos theta minus plus alpha, where R is the square root of A squared plus B squared, and alpha is the arctangent of B over A. So we can see that if we express it in the R formula, we will get 25 cos 2 theta minus arctangent of 20 over 15 plus 15. Now, it doesn't matter what the alpha is. The key thing we're concerned with is the R. Because cosine varies from -1 to 1, the largest it can be will be 25, the smallest it will be -25. Of course, that would imply a negative area. So the maximum area will be 25 plus 15, which is 40. Alternatively, we can also apply calculus. So to find the maximum area, we just differentiate S with respect to theta. ds d theta will give us -30 sine 2 theta plus 40 cos 2 theta. To find the maxima, we'll set the ds d theta to be equals to 0. Then we'll solve this and we'll get tangent theta equals to 4 over 3. Now we have no calculator, we can't evaluate theta, but that doesn't matter. We'll use the reference angle triangle, and we can see that we know all three sides, 3, 4, and the hypotenuse must be 5. So to find the maximum area S, it will be 15 times the cos 2 theta. Cos 2 theta will be 3 over 5, plus 20 times of sine 2 theta, which is opposite over hypotenuse, 4 over 5, plus a 15, and this will calculate out to also be 40. Hence, our final answer must be 40. Question number 7. The diagram below shows three right-angled triangles where BC equals to 14, GF equals to 10, DE equals to 7. We are given that angles BCA, BDE, and FGD are all the same, equals to theta. Find the maximum possible value of AB plus BD plus DF. Pause the video here and give this question a good try. Now, similar to the previous question, you can apply the basic Trigo ratios to express AB, BD, and DF in terms of theta. So in this case, AB will be 14 sine theta, BD will be 7 cos theta, and DF is 10 sine theta. So the sum of the three sides will give us 24 sine theta plus 7 cos theta. Now we can apply the R formula to add up the 24 sine theta to the 7 cos theta. We would get R sine theta plus alpha, where alpha is totally unimportant, and R is the square root of 24 squared plus 7 squared. Now we can find the maximum because sine theta varies between 1 and -1. The area must be between 25 and -25. So the reader is encouraged to try this question using the calculus method as an alternative. Hence, the final answer is 25. Question number 8. If cos x minus cos y equals to half and sin x minus sin y equals to negative 1/3, find the value of sin x plus y. Pause the video here and give this question a good try. Method number 1. Using the sum to product formulas, we can convert the difference of cos x minus cos y into the product of sines. Similarly, we can convert sin x minus sin y into the product of cosine and sine. Now we can divide the first equation with the second equation. A lot of things will cancel away, and what we'll get left is negative tangent of x plus y over 2 to be equals to negative 3 over 2, and we can also get rid of the negative sign as well. So all in all, tangent x plus y over 2 equals to 3 over 2. Now the caveat is that this is not the best method, but it allows me to employ the half angle formulas, which is quite fancy, so I'm going to do that. Now in case you're unfamiliar with half angles, it basically uses the double angle formulas for cosine, but we halve the angles. So instead of cos 2a equals to 2 cos square a minus 1, we write cos a equals to 2 cos square a over 2 minus 1. Now we make cos a over 2 the subject. We will get cos a over 2 equals to plus minus of square root 1 plus cos a over 2. Now notice I put a plus minus in front. It doesn't mean that there are two answers. It means that we probably need to reject one of them later based on the quadrant of a over 2. Next, we can employ the cos 2a identity, the double angle for cosine, but we're going to use 1 minus 2 sine square a, and we're going to halve all the angles. So we will write cos a equals to 1 minus 2 sine square a over 2. Same thing, we'll make sine a over 2 the subject. Again, we'll get a plus minus square root of 1 minus cos a over 2. And why I do this is because I want to produce the half angle formula for tangent. Tangent a over 2 will be the sine a over 2 over cos a over 2. So we're going to divide these half angle formulas together. And this will give us tangent a over 2 equals to plus minus of square root 1 minus cos a over 1 plus cos a. And basically this is exactly the same as what we know of the tangent x plus y over 2 equals to 3 over 2, except that a equals to x plus y. So we now know that tangent a over 2 is equals to 3 over 2. Our aim is to find sine a. So what we can do is we can square both sides. We will get 9 over 4 equals to 1 minus cos a over 1 plus cos a. So we can cross multiply. This will give us 9 plus 9 cos a equals to 4 minus 4 cos a. So we bring all the cosine a's on one side, all the constant terms on the other side. Making cos a the subject, we get cos a equals to negative 5 over 13. If we construct the reference angle for a, you'll see that the adjacent is negative 5, the hypotenuse is 13, the opposite is 12. So sine a will be equals to 12 over 13. Now the more efficient approach is to take the first equation and we square it. This will give us cos square x plus cos square y minus 2 cos x cos y equals to 1/4. We take equation 2 and we also square it. This will give us sine square x plus sine square y minus 2 sine x sine y equals to 1 over 9. Now we're going to add these two new equations together. Notice that cos square x plus sine square x equals to 1. Cos square y plus sine square y also equals to 1. And when we add these two together, we can use the addition angle formula for cosine. Cosine a minus y equals to cos a cos b plus sine a sine b. So when we're adding these two together, we're going to get cosine x minus y. Now, there's still a negative 2 in front, so don't forget that coefficient. And on the right-hand side, we're going to get 1/4 plus 1 over 9, and that will give us 13 over 36. Next, we can simplify a bit. We will make cos x minus y the subject. We'll get 59 over 72. So let's park the result one side, and the next thing we're going to do is we're going to take equation 1 and multiply it to equation 2. So on our left hand side, the cos x minus cos y multiplied by sin x minus sin y is going to give us 4 terms, and be very careful with them. On the right hand side, we'll just get half times negative 1/3 to give us negative 1/6. Now cos x sin x, notice that if I just multiply by a 2 to it, it will give me the double angle formula for sin 2x. So essentially that's just half sin 2x. Similarly, cos x sin cos y sin y is just half sin 2y. Next, we are going to reverse the addition angle formula for sin to give us negative sin x plus y for the last 2 terms. For the first 2 terms, half sin 2x plus half sin 2y, we can employ the sum to product formula, and this will give us sin x plus y multiplied by cos x minus y. And we still have our negative sin x plus y equals to negative 1/6. Now we have a common factor of sin x plus y, and what would be left is cos x minus y minus a 1 when we factorize out the sin x plus y. We already know cos x minus y is 59/72, so we'll get 59/72 minus 1 multiplied by the thing that we want to find, which is sin x plus y equals to negative 1/6. So we'll just divide that away, and we'll get sin x plus y equals to 12/13. And that would be our final answer. Question number 9. If cos A minus cos B equals to half, and sin A minus sin B equals to negative 1/4, find the value of 100 sin A plus B. So this is similar to question 8. You can pause the video here and see if you can solve this question. So we'll use the same trick as question 8. We'll first square the first equation. We'll get cos square A plus cos square B minus 2 cos A cos B equals to 1/4. We'll square equation 2 as well, and this is what we'll get. Now we're going to add up term by term. So the first term, cos square A plus sin square A, will add together to give us 1 by the Pythagorean identity. Same for cos square B and sin square B. For the next 2 terms, we'll have to use the addition angle formula for cosine, and this will give us cos A minus B, and there's a common factor of negative 2. Now we have 1/4 plus 1/16. This will give us 5/16. We can simplify this and make cos A minus B the subject. We'll get 27/32. We'll park this result one side. Next, we'll multiply equation 1 with equation 2. We'll get 4 terms on the left-hand side and negative 1/8 on the right-hand side. Next, we'll use the double angle formula for sine in reverse. So we'll get half sine 2a for the first term and half sine 2b for the second term. Using the addition angle formula for sine in reverse, we'll get negative sine of a plus b for the third and fourth term when we put it together. Now for the first 2 terms, half sine 2a plus half sine 2b, we can use the sum to product formula, and we'll get sine a plus b multiplied by cos a minus b. Now this is good because with the negative sine a plus b that we already have, we can factorize that out, and that's what we want to find, and cos a minus b is already known. It is 27/32. So we'll get negative 5/32, that is 1 minus 27/32, multiplied by the thing we want to find, sine a plus b equals to negative 1/8. We make sine a plus b the subject, so we'll get 4/5, and we'll just multiply 100 on both sides to get 80. And that is our final answer. With that, we have come to the end of video 2b. I'll probably make video 2c on even more Trigo somewhere down the future, but the next one on the Senior Olympiad lecture series schedule will be 3a, and it will focus on the modulus function. Thank you for your kind attention and have a great day of learning.